Hi everybody, it's Mr. Molikash again. This is our video for week 11 for Online Math 171 Pre-Calculus Algebra with Johnston Community College. I'm sorry I put something wrong here and had to cross it out. I guess that's what I get for using pen. But if you have a question about anything you see in this video, shoot me an email. My email is jsmolokach at johnstoncc.edu. Nothing there, just all johnstoncc.edu. All right, this week we're going to talk about oblique asymptotes. We talked about that in our week 10 video, and I'll tell you how to exactly find those today. We're going to review horizontal asymptotes, especially when a function is linear divided by linear. We also made mention of holes last week, and I'll tell you exactly how to find the holes in the graph of a function if it has any. And then we're going to talk about polynomial and rational inequalities. So a lot of stuff in store for today. All right, let's get started. So last week, in our last week video, we were talking about this example, and I'll bring it back from the week 10 video. We were able to find that there's a vertical asymptote at 3 because 3 doesn't make the numerator equal 0. 3 squared plus 2 times 3 plus 5 is definitely not 0. But it makes the bottom 0. So if it makes the bottom 0 but not the top, it's a vertical asymptote. We're able to find our y-intercept by putting 0 in the place of x and getting negative 5/3. And for the x-intercepts, you'd have to use the quadratic formula to find where the top equals 0. And of course not the bottom. So this function, as I mentioned last week, does have another kind of asymptote. It's not horizontal, it's not vertical, it's an oblique asymptote. And the reason for that is because the numerator exceeds in degree the denominator by 1 degree. This is x to the 1 and this is x squared. So you won't have any of these in this class, but if you had, say, x to the 4th and x to the 5th, you'd have the same kind of asymptote. So this has to be 1 bigger in the degree here than 1 in the denominator. So for your class, what you'll have is x squared divided by x. But anybody else who's watching this video, it works for anything like 7 and 6, 7 and 6, 12 and 11, whatever. Okay? So how do we find this m and b in this linear asymptote, right? This slanted asymptote. Well, the way that you do that, and I may have mentioned this in the previous video, is you do long division with this problem. So that'll give us a chance to review the long division process. So what we're going to do is we're going to take x squared plus 2x plus 5 and divide it by x minus 3. You could do this with synthetic division as well, but I'll just do long division. And again, there's no 0 terms here, so everything is counted for. We have linear constant, quadratic linear constant. So I'll just do this very quickly. There's 2 terms in my divisor, 2 terms in the dividend. So I have to put in x here. And I need to find out what number times 1 equals 1, and this is going to be 1. So I get to keep this x, and I'm going to distribute the x like I did in the previous video. Okay, and then what I have to do is subtract. That's right. So we're going to change the signs of what I just wrote down so that the leading terms cancel out. And here I get 5x plus 5. Okay, great. So there's 2 terms. There's 2 terms. I have to put a number in this number column. What number multiplied by 1 gives me 5? And of course that's positive 5. So I'm going to multiply the 5 by the x minus 3 and get 5x minus 15. You might be saying, why is that a 15? Well, the reason for that is because I distributed. I did 5 times x and 5 times negative 3. All right, don't forget you have to add the opposite or subtract so that your leading terms cancel out. And then I have a remainder of 20, right? So one way of writing the function that we're talking about, instead of writing it like this, we could write this as quotient plus remainder over divisor. Okay, I have a startling revelation for you. This part that is just the quotient, okay, tells you the oblique asymptote. Okay, so in the graph of this function, if this were f of x up here and we wanted to graph this, okay, we'd go up and have a y-intercept of 5 and a slope of 1 over 1, and this dotted line, okay, and it would have an x-intercept of negative 5, so we can do that too. Okay, but this dotted line right here would be an asymptote for the function. And as you saw in the previous page, that x equals 3 is a vertical asymptote, right? So this actually helps us graph this function. This helps us graph this function. And let's see, we said that the y-intercept was 0 and negative 5/3. So the negative 5/3 is about right here, right? And so what this graph actually looks like is something like this. It kind of goes like this and gets real close to the asymptote here in a slanted way, and here it becomes sort of vertical. And then there's stuff up here too, okay, on the top of a cross, on the vertical angle where these two asymptotes make vertical angles. You know, that's kind of what the graph looks like, okay? But the key is that this is the equation of this oblique asymptote, and the way that I found it was by doing long division and just grabbing the quotient out of it. So you can ignore the remainder part. In fact, the remainder is the difference between the line and the graph itself. So if I add back the remainder to that line, the line becomes this other thing, okay? So at the end behavior, at x is negative 20 and x is positive 20, the graph certainly looks like a line, but closer in, it's not a line, okay? So, all right, so that's our first objective. That's how to deal with what we call an oblique asymptote. And again, the only thing you'll have to do is quadratic divided by linear, okay? All right, the next thing we're going to look at is to review our horizontal asymptotes. And horizontal asymptotes happen when the degree of the numerator is less than or equal to the degree of the denominator. So here's our function from last week's video, right? The reason why we had a horizontal asymptote is because here the degree is equal. It's linear on top, it's linear on the bottom. So when that happens, all you need to do is divide the leading coefficients. And that's where we got y equals 2 from in last week's video. Okay. Now, again, if you have a constant, if you had, say, a constant over a linear, then remember that's like saying 0x to the 1 plus 6. And so you're automatically going to have the x-axis as your horizontal asymptote. But whenever the top is smaller or equal to the degree of the bottom, so this is x to the 0. So the 0 is less than 1, so it becomes the x-axis. But when they're the same, you divide the leading coefficients. And then remember, the trick is that you can always make them the same, right, by adding 0x to the 1. And 0 divided by 2, of course, is still 0. All right, so that's kind of what happens with the horizontal asymptotes. So now we've seen how to find horizontal asymptotes for constant divided by linear and linear divided by linear. When the top is quadratic and the bottom's linear, you get an oblique asymptote, or sometimes it's called a slanted asymptote. All right, so what kind of graph would have a hole in it? Let's take a look at one of those. All right, so let's say that we have this function. Let's say that we have this function, f of x equals x squared minus 4 divided by x plus 2. Okay, so remember in the previous video we provided some rules for rational functions, right? And you might be saying, oh, Mr. Mullicash, this is the same thing you just did, right? You had a quadratic divided by linear, and so that's going to give you a slanted asymptote, right? Well, no, it's not. Not in this example, and I'm going to explain to you why that's not going to happen. Remember from last week's video that if both the denominator and the numerator are both 0 at the same time, you get a hole in the graph, right? You get a hole at a certain x value, right? And I'll show you what that graph looks like. We're actually going to draw the graph using the hole. So the way to deal with these kinds of functions is to find the zeros of the numerator and the zeros of the denominator. All right, so I'm going to call this top the numerator of x and the bottom the denominator of x. Okay, so let me separate those two things out. This stands for numerator and the other thing stands for denominator, right? Okay, so let's find the zeros of this thing. So the zeros are where, of course, you set it equal to 0, right? And how do we solve this? It's pretty easy. You can just add 4 to both sides and then do the square root. Now, remember when you square root in an equation that there are two solutions to x squared equals 4. One of them is 2, but another one is -2. Sometimes we write plus or minus 2, but for this example, I'm going to separate them, and you'll see why in just a minute. But, you know, 2 times 2 is 4. -2 times -2 is also 4. So both of these are solutions to this equation, and therefore they're both zeros of the numerator. Okay, so let's find the zeros of the denominator. So we have 0 equals x plus 2. Of course, you just subtract 2 from both sides. And look, there's a match. Nope, this is not a video for Match.com, but we do have a match. Both the numerator and denominator are both 0 at the same x value. And when that happens, when they're both 0 at the same time for the same x value, you get a hole in the graph. Okay? So this means, let me go list some stuff over here. This means that there's a hole at the x-coordinate -2. The y-coordinate we don't know yet, but we know that at -2 there's going to be this weird thing in the graph called a hole. Okay? It's interesting to find out too that because of this, because this is the only 0 of the denominator, there's no other ones, that there's no vertical asymptotes. In other words, there's no way that the denominator can be 0 and the numerator not be 0, because there's only one 0 in the bottom, and it's this, and it matches with the top. So the only way you can get a vertical asymptote is if you find one of these that doesn't match with one of these in the top. All right, so this means there's a hole. Okay, when it's a 0 only in the numerator, this is an x-intercept. This is an x-intercept. And if we had anything left over down here, this would be a vertical asymptote, but we don't. Okay? All right. So we'll list this as well. The x-intercept is 0, 2. Okay. So there is no vertical asymptote, and of course there's no horizontal asymptote either because the top had a bigger degree than the bottom. All right, so now all we have to do is find out what the y-coordinate of this is. So the way to find the y-coordinate is to try to simplify this fraction. And the way that we can do that is by factoring. So we're going to factor the numerator, and the denominator is already a linear factor, but remember this is a difference of squares, so this is x plus 2 times x minus 2. And here's another piece of evidence where there's a matching 0, right? There's a number that makes both the top and bottom 0 at the same time, and that's it. -2 is it, right? But if we simplify the fraction, we can cross these out, and we can say that f of x is x minus 2 as long as x doesn't equal -2. But you say, wait a minute, why'd you have to put that there? The reason I had to put that there is because if I put negative 2 into this function without anything canceled, what's the value that I get out of it? If I put negative 2 in the place of every one of the x's, I get 0 times negative 4, which is 0, and on the bottom I get 0. And 0 divided by 0 is undefined. That's the reason there's a hole in the graph. But down here, if I put negative 2 in the place of x, I don't get undefined, I get negative 4, right? So, negative 4, if I put x is negative 2, is not in the domain, but f of negative 2 is negative 4. What's this? This is the y value of the hole. And I'm sorry if this is terribly hard to read down here at the bottom, but anyway, I'm writing f of negative 2 is negative 4, and that's the y value of the hole, right? Now, it's not negative 4. F of negative 2 doesn't exist, but just kind of pretend that you're putting it in there anyway, right? And so what we're going to see is that this point, negative 2, negative 4, is not a point on the graph of f. It's a hole, right? All right. So what does the graph of this thing look like? Let's say we wanted to graph this. Well, the graph would look exactly like this graph, except it would have a hole in it right there. So remember what, the graph of x minus 2 is pretty easy. It's y-intercept negative 2. And then the slope is positive 1, so you go up 1 over 1. But at negative 2, negative 4, there's going to be a missing point in the graph. And I'm going to try to draw that as an open dot on the graph. So I can draw the line everywhere except where that hole is in the graph. Okay? So this is the graph of y equals f of x. Now, if I didn't put that x not equal to negative 2, I'd be able to draw the whole line. It would just be your standard y equals mx plus b line with nothing wrong with it. But in fact, what this is that this is a line with one x value removed out of it. Okay, so these two functions are the same only when x is not negative 2. So when x is not negative 2, we're good, but when x is negative 2, there's a hole in the graph. Okay, so that's kind of what you have to deal with when there's a matching 0 in the numerator and denominator, and that's what provides a hole in the graph. So that's what we are dealing with there, and you're going to need some practice with that to get good at those. So hang around in Alex for a while. Don't rush through the objectives. All right, so our next objective now in this video is to find out what a quadratic inequality is, right? So a quadratic inequality is, how we have a quadratic equation, right? Quadratic equation is, well, we have a quadratic function that looks like this, right? And the quadratic equation is when we can put everything equal to 0, right? So this is a quadratic function. This is a quadratic equation, and the solutions to that are the quadratic formula, x equals negative b plus or minus square root, all that stuff. So what we want to do is, instead of having it equal 0, we want it to not equal 0. We want it to be less than or greater than, or possibly less than or equal to, or greater than or equal to. All right, so how does that work out? Well, this is an example. So here's an example that shows you how to do that. Or deal with that. So say x times x plus 1 is less than or equal to 2. All right, so we want to solve this, right? We want to find out what all of the values of x are that make this left side either equal to 2 or less than 2. Well, the first thing we're going to have to do, just like you used to do with equations, is make sure that one side is 0. Another thing is that this is factored right now. We need to multiply this out so that it looks more like the quadratic expanded form. So the first thing I'm going to do is expand the left side by distributing the x. And then I'm going to subtract 2 from both sides as well. Okay? Now, the next thing I need to do is find the zeros of the quadratic function. And I can do that by factoring. If you can't factor, then you need to do the quadratic formula and spend a lot more time on this. But this one factors. So 2 times 1 is 2. I need the numbers to have opposite signs so that when I multiply I get negative 2. And then I have to have the 2x and the 1x make positive x. So that means that this 2 gets a positive and this one gets a negative. All right, so the 0 of this is x equals negative 2, and the 0 of this factor is x equals positive 1. Okay, so first step is make sure that everything is equal, or one side is equal to 0 and the other side is quadratic. You want to find the zeros of the quadratic. All right, next step is to put these zeros on a number line, and I'm going to put them in order from least to greatest. So if I had the plus 1 here and the minus 2, I still put the minus 2 first. Okay, and so what are these? These are the x values. This is sort of like the x-axis, the number line. Okay, so what I'm wanting to do now is I want to put some test values into this factored. You can use the unfactored version too, but you definitely want to use one of these, not the one up top. Okay, don't use that. So we'll pick some numbers that are in these intervals. First one has to be strictly less than negative 2. Another number that we'll pick is between negative 2 and 1, and the last number we'll pick is bigger than 1. So we'll pick a number here, a convenient number like negative 3. Okay, now if I put negative 3 in for x, I get negative 3 plus 2, which is, that's x. So f of x is negative times another negative. Okay, let's kind of do some mental math here. Negative 3 plus 2 is negative 1. And negative 3 minus 1 is negative 4. So if I put negative 3 in, I get a negative times a negative, which is a positive. So this entire part of the number line is not going to work, because remember, we wanted less than or equal to 0, and this positive is greater than 0, right? Now, while I'm here, I'm going to definitely use negative 2. If I put negative 2 in, I get 0, and I can equal 0, right? So I'm going to close that dot in. I want that dot to work, and the 1 as well. Okay, both of these numbers are part of the solution. They're not the only numbers that work, as we're going to find out. So we're going to put some numbers. Let's pick a number between negative 2 and 1. Real easy one is 0. If you put 0 in, you get 2 times negative 1, which is negative. So bingo, we want all of these numbers to be part of our solution. Everything between negative 2 and 1, including negative 2 and 1. The reason for that is because negative numbers are good. They're less than 0. And these other numbers that I put dots at, they're good because this makes the left side equal 0. So let's figure out what's going on over here. We'll pick some number, maybe 2. It has to be bigger than 1. I could pick 200 or 2 million, doesn't matter. But when I put 2 in the place of x, I get a positive and then another positive. This turns out to be positive. Okay, so I don't want those uncolored parts of the number line. I want this one. So in set builder notation, I'd say that the solutions are x such that negative 2 is less than or equal to x is less than or equal to 1. In interval notation, and you're certainly familiar with that by now if you're watching this video, the interval would be from negative 2 bracket to positive 1 bracket. And the reason why the brackets are there is because these are equal. So if this was strictly less than, these would both be open circles, those wouldn't be there, and these would both be parentheses. So just kind of watch out for that. All right. So that's what we deal with quadratic inequalities. So what if you have a higher order polynomial? Well, the same rule applies. In a higher order polynomial, you just have more zeros. So if it's not factored, you're going to have to factor it. You'll have to provide more factors here, and you put more numbers on your number line and you test more values, but it's the same thing. Okay, so if it's not quadratic, you just have more factors to deal with. But I can't emphasize this enough. Test each and every interval. Don't assume that they're going to change plus minus, or minus plus or whatever, because they may or may not change. And there's rules for that. You can look these up online or in the book or in ALEKS if you want. But make sure you test numbers inside every interval and put them back in and see if you get a plus or a minus. And then the pluses would make it positive. So if this said greater than 0, I'd want those, right? So, just something that you need to really practice with. Factoring is super important. Otherwise, you're going to have to deal with the quadratic formula. And if the thing is cubic, the quadratic formula isn't going to help you. And don't look up the cubic formula either, because that is a nasty mess. All right, our last example for today is what happens when you have a rational inequality. That's this thing, a rational inequality. So we'll finish off our video today with that. So here's an example of what I mean. We'll have a rational function, and this time I'll make the denominator different. And we'll say I want this whole fraction to be greater than or equal to 0. Okay, so let's solve this inequality. And again, we want to find out every single value of x that makes this left side greater than or equal to 0. So similar to what I did when I found the wholes, I'm going to separate the numerator and denominator. I want to find what's the numerator. The numerator as a function of x is x squared minus 4. The denominator as a function of x is x plus 1. I'm going to find the zeros of both. Okay, so here, refer to earlier in the video, remember that those zeros were 2 and negative 2 when we did that math. Over here, if we solve this one, it's pretty easy. We get x equals negative 1. All right, so this time, like we did before, we're going to take all the zeros in our collection from the numerator and the denominator, all of them, and put them on a number line like we did in the last example. And it's important to put them on this number line in order from least to greatest. Okay, so negative 2 is going to go first, and then negative 1, and then later on we get positive 2. And what I'm going to do is I'm going to do the test values for x. So we're going to put some different numbers in for x, and then we'll figure out what's going on with f of x. And f of x is the left side. Okay, I'm sorry if I didn't define that very well earlier. All right, so let's pick some numbers. So maybe we can pick negative 3 here, negative 1.5 there, 0 would definitely work here, and maybe 3. And these numbers are arbitrary. I could have picked 1 or 1.98 or something like that. So, I'm picking convenient values. Whatever number you pick, it will give you the same plus or minus result no matter where it is in this little interval here, okay? So these numbers, there's nothing magic about these numbers that I picked. All right, so let's do some mental math. If I do negative 3 times itself, I get 9. 9 minus 4 is 5, which is positive, right? Divided by negative 3 plus 1, that's negative 2, so that's negative. And a positive divided by negative is a negative. I don't want that. I want it to be greater than 0. So let's just keep plugging away. If I put negative 1.5 in here, I get 2.25 minus 4, which is negative. And then negative 1.5 plus 1 is negative. When I divide two negatives, I get a positive. And so these numbers are good, right? So I'm going to color in at least the interior of the interval here. Now, while I'm here, let me explain something very important. Remember how we said that the zeros of the numerator are x-intercepts? So x-intercepts are zeros of the entire function. So because this is able to be equal to 0, I'm going to color that in. In other words, if I put negative 2 in all the x's, this entire thing is going to equal 0, and that's okay. But if I put negative 1 in the place of x, remember, this number's 0 of only the denominator, so this is a vertical asymptote, which makes the function undefined, right? So I can't put negative 1 in the place of x. And even if I could, it's not going to make this fraction equal 0. It makes it undefined. So don't use negative 1, okay? All right, so let's keep on rolling here. If I put 0 in the place of x, that just erases all the x's, so I get negative 4 divided by positive 1, which is negative, so I don't want those. And then if I put 3 in, I get a positive divided by a positive, which is positive. So that's good. I can use everything past 2, including the arrow, right? Everything past 2. And what's at the end of the arrow? Infinity, right? Infinity. So now, question. Let you think about this for a moment. Should I color this value in or not? Okay, the answer is yes, I should color it in, because at positive 2, this fraction equals 0, and it's okay to equal 0. So, all right. So, what are the values that we want? Well, I'll do the interval notation first because it's easier to read off of this graph. So, we want to include negative 2. We don't want to include negative 1, so we do that. The stuff that I colored in is part of the solution. Over here, I'm going to union this with bracket 2 comma infinity, and you never put a bracket in infinity. All right, so this is the solution in interval notation. If they ask you for set builder notation, this would be negative 2 less than or equal to x less than negative 1, or x is greater than or equal to 2. And this is a little bit more awkward to write, so more than likely you're going to be asked to write it in interval notation. Okay, all right, long video, sorry about that, but that's just one quick example of a rational inequality. They do get a little weird, they get a little bit more challenging, so if you have any questions, do shoot me an email. Remember that my email address is jsmookach@johnstoncc, no junk between, .edu. Thanks so much. Have a great week.